I think this is page 9. Let's take a couple of minutes before we start. Okay, any questions? Okay. Okay, what we're going to cover today is a little bit more on gamma xy square. Okay, what is the gamma xy square? What does it do? We live in the world such that there are lots of noise here in the world. So we really like to know the level of kind of containment in the world. Like if you go to airport and stand there, when the airplane takes off, tremendous noise is there. I think it's about 100 dB, it's very high. And we really like to know the true signatures and the true output, and of course noise contamination level. So this gamma xy is the measure of noise contamination in the system. A lot of time noise contribution is so high that we really don't know what the real signature, which means input and output, the response. So that's what the gamma xy square, which is called the ordinary coherence function, which is gamma xy square. Okay, so that's what I introduced. The equation form is gxy absolute square divided by gxx and gyy. That's what the gamma xy is. So here is gxy absolute square divided by gxx, gyy. Of course, this is in frequency domain. Gamma xy absolute square is a real value. It's not a complex. Absolute. And this xxyy is a power spectral density function, or the auto spectral density function. That's real, no phasing. So, or you can use as S. This is the valid region of frequency. Here is 0 to infinity, right? And here, when you use two-sided spectra, what's the range of the F? Gusto? Here, from Jakarta to Seoul. In other words, from minus infinity to infinity, right? Mathematical expression is very popular to use. And the range of gamma xy square is from 0 to 1. If gamma xy square is 1, what does it mean? Gamma xy square is 1, no noise, okay? So most ideal situation, no noise, when gamma xy square is equal to 1. If gamma xy square is equal to 0, only noise. There is no real signature coming into it because it's just masking. Everything is noise. And not Monday, we talked about how to handle the mean value, right? Mean signature. First, take away from this dynamic signature the mean value, which is a static value, happening at f is equal to what value? 0 value. Static, DC, okay? Take away the DC value from AC. AC is alternating, which is actual current in electricity. And for the ideal system, of course, ideal system means no noise. So gamma xy square is, this value is g xy absolute square, right? Right. And this is a gxx, gyy. Gxx is as is, and gyy, you can express gyy equal to h absolute square gxx. Now this is about time you should get very familiar with the relation, spectral relation between the input excitations and output response. Okay, I'm demanding. So this is what happened, then this has to be equal to 1, which has no noise. Okay? And if x and y are uncorrelated, x, 여친, y, 남친, no relations, okay? Then you declare the baby will never be born. Uncorrelated. So if it's uncorrelated, cross-correlation function, gxy, has to be equal to 0. No boys, no child. gxy, x and y has nothing to do with each other. Then cross-correlation, the cross-spectral density function gxy is equal to 0. That's what we all covered already. So which means this value in the numerator, gxy absolute square is equal to 0. So gamma xy square is equal to 0 if y does not produced by the x. There is no relation between x and y, which means that gxy has to be equal to 0. Okay? Usual condition that the gamma xy square is between 0 and 1. Usual conditions, okay? Usual conditions, extraneous noise is present in the measurement. Extraneous noise, some foreign noise, noise coming from outside with some other source, not induced by x or y, then that's extraneous. Foreign noise, then of course gamma xy square is equal to 0 as you measure. Another situation which will happen in actual measurement in the reality is this. I bet you have experienced the resonance situation. Resonance situation means when excitation, when you do the sinusoidal sweep, what that means is you have, sorry, I don't have any experiment to do. I have a plate, I have a shaker, I have a transducer mounted to take a measurement. Then when you apply the sinusoidal forcing function, then it will excite the plate by the shaker. As you change the frequency for sinusoidal function, as it sweeps the frequency range, let's say from near zero to some the destination frequency, it will hit the resonance, right? In other words, excitation frequency is approaching to the first fundamental frequency, right? When it sweeps. Then at the resonance, right at the resonance means when excitation frequency hit the fundamental or lower frequency of the plate, then suddenly resonance occurs. What does it mean resonance occurs? For the small amplitude of excitation at the resonance, you don't have to put much energy to excite the plate, for example. With a small input excitation level, it vibrates very hard. Okay, for small input, there is more tendency to have a noise than a heavy excitation. So whenever it hit the resonance, in the plate could have many resonance situations, okay? How many the resonant frequencies for the given plate could have? Stupid question. How many resonant frequency? Depend on the natural frequency of the plate. It could have many resonances, right? But as it goes to higher frequency, the amplitude of the response, for example, amplitude of the plate vibration, as F is a lower frequency region, excitation, the amplitude of the plate motion is a little bit larger. As it goes to higher frequency, what that means, number of oscillation per unit time has to be very high, but which means amplitude has to be very small. So you have more chance to introduce a noise in the system. So for such the plate, for example, it can hit the many resonant frequencies. Whenever it hit the resonance, of course, there is so-called the dip, resonance dip there. Even if input excitation is small, even small, then it excites the system much higher. That time you have spectral value at that resonant frequency, it drops, which means gamma xy square drops right at resonance. Remember, right at resonance, especially for lower frequency at the resonance, it just dip much deeper for gamma xy square, which means it introduces a noise in the system more, for example, then gamma x square is below, of course, way below the 1. That's the situation. It phases for this. The gamma xy square stays in this range. Some resolution error could involve when the x and y are the nonlinear. It happens also. And the y is due to other input beside x. it happened, because this is really showing the relation between X and Y. Okay, but usually this is really for the situation gamma xy square is less than or equal, less than 1 really. Whenever this value is less than 1, then usually you have to find out what's the source of noise contamination. What's the reason to get the gamma xy square is less than 1? So you have to investigate. Very important. Okay, and for next 3 topics within chapter 4, single input-output relation, we're gonna really introduce or inject the noise in the system. There could have a noise in the excitation input. The noise could be in the output system, output transducer, input transducer. And another situation could be the noise could be introduced in the input and output, and how to handle that. And sometimes noise in the input can transmit through the system, or the noise may not go through the system because it could happen in the transducer, right inside the transducer. And inside the transducer, you can have electronic noise in there. So considering many situations, what I'm going to do here is what happens if the input is introduced, if the noise is introduced in the input. And what happens if the noise is introduced in the output only? What happens the noises are in the input and the output? What happens if the noise introduced in the input passes through the system? So lots of different situations you can think of. So remembering is not going to work to solve the problem. To get, for example, to get the transfer function or frequency response function, you have to fully understood the logics of it. Okay, that's what really second part of the lecture belong to. Second part of the lecture, get the logics, then any situations you can handle that. So in this case is a model, which means a system model with output noise only. At output, N is output, but it's uncorrelated noise. Uncorrelated noise is this noise, output noise, I'm using small n in time domain. And I just introduced as a signature coming from the third source. It's not connected to the Y. Y did not generate the N. N just came in from the third source. Then how that noise contribute in the system, in the H transfer function, for example, or GYY, where that noise term goes into. So detection of the noise is the goal. What happened to noise? I want to eliminate the noise to see the real signature. Signature means the signal, no differences. H is the system. H is the system. What that means, H is a propagation path dependent the transfer function. So you have a shaker, you have the transducer to measure it, from the large system or plate or build-up structure whatsoever. Okay, so this path from here to here is path-dependent transfer function. Okay, so H is that. That's really transfer function in the system, path-dependent. And of course, X is input signature, like coming from the shaker, which you put right on the system, or from some other motors. Okay, if you look at the ship system, I'm always dealing with the naval system. That's what I have been working in the past. About 10,000 ton ship, naval ship, has about 600 motors. That's a lot of motors. Maybe a larger aircraft carrier may have over 1,000 motors. I'm talking the destroyer class ship has about 600 the motors. And the X could be such a vibration source generated. And then the H is a structure, could be a structure system, ship systems, upper deck systems, whatever. And V is unmeasurable. Unmeasurable, the output, this could be, this is a transducer. I use a summation sign for transducer. Have you seen any transducer? Today, in mechanical engineering, do they have any measurement course? Sometimes take a measurement course, engineering measurement course. It introduces all fundamental things in measurement. It's a transducer. Transducer means like a accelerometer, 가속기. All different kind depend on the dynamic range of acceleration to measure. Some are pretty big. To measure the acceleration of a big build-up system, you need a larger, but which cannot measure higher frequency. It has to be lower because mass loading is pretty big. Some are very small because this build-up system is a pretty light system. Then you want to measure the high frequency response. Then that time I used a small Endeavour accelerometer, which measures pretty high frequency range the motions. So size depends on the frequency of interest and of course amplitude of the motions. So this is a transducer. Accelerometer, velocity meters, strain gauge, you can put that as a summation sign, but I usually express this sign for transducer. Actual gauge to put it on. And Y is the total output of a transducer. This is before you measure the transducer, so no signal in the transducer is involved here, just put outside here, which means noise is not part of it. It's a pure, V is a pure output from the system. Okay? I think it's clear. So if I want to put just before the dot, and if I use a U, T, which is input, pure input signature, and this is a pure output signature. This transducer, when you measure, you have to put the transducer. Otherwise, how are you going to measure? So here, the measurable, in this system, the measurable signature is, of course, X is measurable. And V is not measurable. V, the Y is measurable. N is not measurable. It's a noise. Okay? So it's not measurable. But this, I said, here is uncorrelated. That means G, Y, N is 0. The G, V, N is equal to 0. G, X, N is equal to 0. It's a standalone. It's a single. Okay, so never married. But a very strange guy hiding behind, that's a noise. Okay. So here, Y, this is a time domain signature, small letter, lowercase. Y is equal to the V plus N, isn't it, right? It's clear. And Y is equal to capital V plus capital N. I just eliminate the things in the parentheses, right? Things in the parentheses, what does it mean? F, comma, T, we all know that. So we are not going to bother to write that here. This is in the frequency domain. So X star Y is V plus N. So Y star X star Y is X star V plus X star N. This is the way I put it out, the expression using the G, okay? So this is a Fourier transform notation using FFT routine. You can solve this problem as like this. G xy is equal to G xv plus G xn. Xn, Gxn is equal to 0. Why? What's the reason? The N is uncorrelated noise. That's why spectral function which include N noise is equal to 0. So you can tell Gxy is equal to Gxv. If you look at this, Gxy is equal to Gxv because noise is uncorrelated, doesn't come into picture. And of course, Gxy is equal to G, the H, times the Gxx. Why? Well, Gxy is equal to, the H is a transfer function, times Gxx as is. I don't think it's right here. It's even derivation is here. The next page I can skip all such a basic operations and showing the result right away. So here is a GYY is equal to ZVV plus GNN. It's right here, which is coming from here. And the GVV here, look at this point to that point. ZVV is equal to H absolute square times GXX. Is it clear? I insisted 2 equation set to remember. GYY and GXX. Repeat. again here because it's all based from there. This is yt. Xt. Tell me the frequency domain, the expression, two expression. Maybe Jeremy can tell me the two expressions I insisted the other day. Not memorize, just remember as your baby. Jebam, you remember SXX is equal to what? I'm sorry, SYY, output, is equal to? Yunso, input-output relation, that's all I'm saying. Look at me, not that, look at me. Huh? H absolute square? X. This is all time domain. Okay, Gustav, what about the SXY? It's all frequency domain. What is it? As H. This two, based on these two. One more equations I just covered. Gamma xy square, which is in frequency domain, is equal to what? Youngbin, what's this? In terms of S or G, top G, right? X, Y, right? What about here, two term in the denominator? GXX and GYY, that's it. This is real. That's about all. Then you mess around in the frequency domain, then you have a beautiful relation. So that's what's true. Okay. So here, if you look at the true output V is right here. Okay, YY is right out there. After noise is included, VV plus NN around the output here. Around here, X is the same, V replaced by Y, so you can tell right here, GVV is equal to H absolute square times the GXX, or GXV is equal to the H times GXX. Some relation you can develop based on nothing but this relation. Okay? Repeat over and over again. That's about it. So GVV H absolute square GXX. Okay? This is auto spectra, not the cross spectra. Then GXY, look at this Fourier transform expression, then you can zap, right? Then that introduces right there. This is same as what I've shown here. So GXY is equal to GXV is GXV is equal to GXY. So it's GXY is equal to GXV. GXY is equal to simply this is a relation between from here to here. This is uncorrelated, so you can delete that, then comes right here. X correlate to directly to y, you can express. So gxy is equal to the h times gxx. I think that's about it. So gxy is h times gxx. And GVV is equal to h squared times gxx. So h is gxy over gxx is right here, times the gxx right. So I want you to, if you really sunk into it, then you will confuse. So just to put it away and look through, then all we are using is this two relation with the gamma xy square, nothing more. Pay attention on whether noise is coming from the system or outside the system. Then outside, way away, noise is coming from way away from the pump, away from the system, then that's the uncorrelated. What does it mean, uncorrelated signature? Uncorrelated. It has nothing to do with the system or part of the system. It's coming from the other source. So by looking at that, by looking at this is what this result is, right? So here, what's the measurable? What is the measurable here? GYY is measurable, right? And the gamma XY square, is it measurable? You can compute based on the measured data, which means measurable, right? If you look at the instrument, dynamic signal analyzer, then there is a button always, the coherence function. That's what the gamma xy square. Of course, internally, they use a measured data to get the gamma xy square. So it's a calculatable using the measured data. So this is measurable, this is a calculatable. Then GVV, you can calculate GVV. Okay. You cannot directly measure the GVV, but you can calculate. So gamma xy square is G, gamma xy square is GVV divided by GYY. If you do that, which is 1 minus GNN over GXX. Okay. Expression-wise, 1 minus GNN over GYY. Look at carefully here. Is the gamma xy square calculatable? Yes, it is calculatable. Gamma xy square is equal to 1 minus GYY. Is it measurable, Gusto? Yes or no? Yes, measurable. Then GNN, which is the noise spectra. Can you get the noise spectra? Yes, you can, because you know this function, you know that function, then GNN is calculatable, right? Which is you switch around here, GNN, which is in frequency domain. GNN is equal to what? So GNN there is equal to 1 minus gamma xy square gyy. Is it true? Switch it minus, yeah. So you can calculate this guy, measurable. Well, calculatable, measurable. Then you can compute that. So I usually ask the situation in the system, then compute the noise spectrum. Noise, power spectra, density function for noise, and plot it. Then you can tell what would be the level of noise contamination. It's a frequency-dependent noise contamination. Okay. GNN is output noise spectra, right? Output noise. This is output signature. Noise over signature. Noise to signature, which is called the noise to signature ratio. Very typical way of saying that, which is not noise over signature, is a spectra expression. Noise spectra over the output response spectra, expressed in the auto spectra or power spectra, which is always called noise. In this case, it's output noise to signature ratio. If you use M, usually use M in the input noise. So if this is M, GMM over GXX, X is in the input, M, small m stay in the input, then that's input noise to signature. You will never use like a GMM. You will never use GNN over GXX. Doesn't mean anything. GMM over GYY. You never use this kind of the expression. Noise in the input side, you have to compare with input signature X. For the output Y, you have to use the N. Okay? Very clear. So if this is equal to 1, that no noise contamination. If it's equal to 0, there is full of noise. Okay, this is with output noise only. Then what happened for the input noise situation? Input is M, okay? And this is one case, okay? But if you use, if you understand the one case, you can virtually do any situation. So anyway, this case is the system model with input noise only, input. And this is all made up the diagram. So in this case, let's say the M, I put the arrow here, means is really the inside, I can make up the reasoning. Inside the transducer, there is a sort of the electronic noise in the transducer, which doesn't propagate into the system but stay in the transducer itself. Okay, so that case M stays in, but from the transducer you have to take out the measured the signature, which is X. And really the input signature which transmit into the system is U. Okay, so what happened is U is the signature which transmit into the system. U is the signature which transmit into the system, but M stays here. So M just happened within that transducer. So it's not correlated to Y. This is not correlated to U. Okay? So M plus U is equal to X. Got it? Yes, got it. So here I said M does not pass through the system. We're going to study the case the input noise passes through the system. Okay, then once you learn all that, then I can make it any diagram I expect you to solve the problem for designated spectra. Okay, then after that you can really do anything. But still, as I look back, still some students has difficulty because didn't understand the logics. That's the reason. If you once understand the logic, easy. So X is equal to U plus M. Okay. Next week, I'm gonna, as a part of the diagram, I'm going to introduce the feedback, negative feedback system. I want you to, I checked just before I came down the internet, I just type in negative feedback system. And I want to know what information it provides. It provides very, very good, all the necessary information. I want you to do the same thing. That makes my life easier to explain. There are a lot of cases for negative feedback system. Would you mind to look at in internet? Just type in negative feedback system or negative feedback. Then you will see quite a bit of information. But just to click couple case, then just to read and come back. Then I can tell you easily. So here is X is equal to U. This is so detailed. As you look line by line once, then you will understand. That's all it requires to solve for the effect of the input noise to the system, to the output. So over here, X is equal to U plus M. Is it clear? Yes, it's clear. X is input, measurable input, okay? M, you can't measure M, which is part of it. Then XX is equal to U at G. GXX is equal to G UU plus GMM. Is it understandable fully? This is uncorrelated, independent each other. U doesn't generate the M. Okay. Then GXY is equal to GUY plus GMY. my may not be clear. So that's why I put this guys in the frequency domain function. X star, X is equal to, in frequency domain, capital X is equal to capital U plus capital M. Then conjugate, then multiplied by y here. Then express in the spectral notation. Gxy is equal to Gui plus Gmy. Gmy is equal to 0. Why? Input noise has nothing to do with the output response. This guy, input noise, Gmy, has... I'm doing here, yeah. Okay, Gmy, output noise, output signature, and M has no correlation between, because in this case, M doesn't pass through the system at all. So I can comfortably say Gmy is equal to 0, which means that Gxy is equal to Gui, because M doesn't come into picture. Rather than going through to Y, I can just say U through the Y. U through the Y, very clear. So Gyy is equal to H2 times the GUU. GUY is equal to H2 times GUU. You see that relation right away? It's right here. You can delete. So this is over here. GUY is equal to H2 times GUU right there. So GXY times H2 GUU. So gamma XY square, if you always go back to the definition and final destination, if you see that, you have boxed relation, gamma XY square is equal to 1 minus GMM. This is GMM, not GMN, GMM over GXX. Gamma XY square, you can calculate based on the measurable quantity. GXX, measurable quantity. GMM is calculatable using the measured and the calculated the result. This is a frequency domain. It's a function of F. So you can do the input noise spectra, you can compute output noise spectra. You plot the GYY, which is output the spectra. Then you can plot the GMM or GNN. Then you can plot the input-output noise. You can tell how much noise contamination in various frequencies are there. You can compute that, saying, well, this particular system we got problem because you have a loss of noise coming from the input side or output side, or transducer could be something defect in there. We have to change to a new transducer, vice versa. You can determine the things to take the action. Okay? So this next few pages important. I'm always saying the important. But this is very compact lecture note. So that's what I want you to study. Okay, so I'll see you Friday. Friday, what time does Jokku start? This is Friday, isn't it? What? 4 o'clock? 2 o'clock? Okay. 2 o'clock. Okay, we have to move out, so they can coming in. Alright, so I'll see you Friday, 1 o'clock. And I'll give you my experiment videotape sometimes, not today, so we'll do that.